Right, so now we're going to diagonalize a 3 by 3 matrix. Of course, if it's possible, every matrix is not diagonalizable. So we'll talk about that later. So let's find the eigenvalues. So I need to subtract lambda from the main diagonal. And find the determinant. So we'll have to use cofactor expansion here. I don't think there's any way out of picking a better row than the other. Let's just expand this first row. We'll just have to work it all out. So I get 1 minus lambda times determinant of -5 minus lambda 3, -3, 1 minus lambda. And then minus 3 determinant, -3, 3, -3, 1 minus lambda. And then plus 3 determinant, -3, 3, -5 minus lambda 3. So this first determinant is -5 minus lambda times 1 minus lambda, and then plus 9. And the second determinant, it's -3 times 1 minus lambda, and then again a plus 9. And then we've got the last determinant is -9 minus 3 times -5 minus lambda. So we're going to get this big polynomial here. I guess I shouldn't have written determinant there. So I need to full this out. So -5 plus 5 lambda minus lambda plus lambda squared plus 9. And distribute -3 plus 3 lambda plus 9. And distribute here, get plus 15 plus 3 lambda. Simplify. So we really need to multiply everything out. I don't see anything that is going to help us in terms of factoring. If I had a common factor in all 3 terms here, then maybe I could do something, but I don't. So I'm just going to have to multiply everything out. So I've got lambda squared plus 4 lambda plus 4 minus lambda cubed minus 4 lambda squared minus 4 lambda minus 9 lambda minus 18 plus 18 plus 9 lambda. Well, good. We got some stuff canceling out here. Actually, all of this stuff cancels out. I should have noticed that this was negative and positive. Okay, well, we get 1 minus lambda plus 2 squared. Right, I just went back to this part. 1 minus lambda, and then this guy is a perfect square, lambda plus 2 squared. So we'll say lambda equals 1 and lambda equals -2 with multiplicity equal to 2. So that just means we have a double root. We have 2 roots of -2. And that means that I only have one eigenvector or one eigenvalue here where, maybe I should have 2. And I'm going to hope that I get 2 eigenvectors out of this guy. All right, so for lambda equals 1, I need to solve A minus I x equals 0. Just plug it in 1 for lambda. And I've got to subtract 1 from the main diagonal. So that would be 1 minus 1 would be 0, -6, 0. And then the rest are 3s and -3s. So I just need to row reduce this. I'm going to use a calculator. So I get 1, 0, 0, 0, 1, 0, -1, 1, 0, and then column of zeros. And I only need one example of an eigenvector. So x1 is x3, x2 is -x3, x3 is free. So let's just let x3 be 1, and I'll get the eigenvector 1, -1, 1. All right, so now let's look at lambda equals -2. I need to solve a plus 2i x equals 0. So instead of subtracting 1 like we did last time, we're going to add 2. And of course, augment with 0. All the other stuff is going to stay the same. Just the main diagonal. So that would be 3, -3, and 3. Right, I just added 2 to these main diagonal entries. And I got 3, -3, and 3. And this one, I don't need a calculator to row reduce this. Right, I'm going to get 2 rows of zeros. Divide the first row by 3, I get this. So this is good news. So I get 2 free variables now, which means I can get 2 independent eigenvectors. And it's important that you get independent eigenvectors. So for this eigenvalue with multiplicity 2, I'm going to get 2 independent eigenvectors, and that will let me fill out the diagonal matrix in the matrix P, such that P has an inverse, right? P has to be invertible. So the vectors I put in there have to be independent. If you don't get 2 here, if your eigenvalue has multiplicity 2 and you only get 1 eigenvector that's independent, then that matrix is not diagonalizable. So your multiplicities has to equal, the dimensions of all of your eigenspaces added up together, or how many free variables you get total has to equal the same as your multiplicities. All right, so x1 equals -x2 minus x3. x2 is free and x3 is free. So let's just do parametric vector form, and I'll just use these 2 vectors that I get. So here I get -1, 1, 0, and this one is -1, 0, 1. So I'll use these 2 vectors for my matrix P. All right, so I need to decide D first. So one eigenvalue was 1 and the other one was -2. So if you have multiplicity 2, you're going to have to repeat that eigenvalue in your diagonal matrix. And for the matrix P, I just got to make sure that I put the eigenvector for lambda equals 1 first. So 1, -1, 1 has to go first. The other 2 for -2, it doesn't matter what order they go in as long as they're second and third. Right, so there is my matrix D and my matrix P. to use in diagonalization.